All right, thank you, Milos. Hopefully everybody can see and hear me. I say good afternoon and evening from Jacksonville, Florida. For the brief time that we have today, I would like to talk with you about the differences between physical and visual comfort and how they are critical for the overall patient satisfaction with contact lenses. I understand this is going to be translated into several different languages, so I will try to speak clearly and at a good pace, at a moderate pace. Okay, so let's just jump right in and talk about physical comfort. And what I mean about physical comfort with contact lenses, I mean more of the tactile responses, such as dryness and lens awareness, grittiness, burning, those type of sensations. Okay, so what is comfort? It's kind of funny to think about it sometimes. Is it simply a lack of discomfort? Do we ever describe a contact lens as being comfortable because it's not uncomfortable? And I don't think so. And actually, the literature agrees with that. The absence of discomfort does not automatically result in comfort. And in fact, comfort will be felt when more is experienced than expected. So does discomfort equal pain? Well, almost. Discomfort is really, just being uncomfort is a precursor to experiencing pain. And, right before being uncomfortable, we also have another type of thing that it's listed here as just being unpleasant. But in our research area, we actually think about this as what we call just noticeable differences. And that actually plays a role here coming up that I'll discuss with you. But just noticeable differences are precursors to being uncomfortable, which are precursors then to feeling pain. And of course, the biggest thing with pain is you actually have the potential or actual issue of potentially causing tissue damage. So I got one slide here that I just want to talk about, how do we measure physical comfort? Well, yeah, we do it with questionnaires, or the other word is called patient-reported outcomes, or PROs, that are used all the time in clinical research and in clinical practice. So the two main types of scales that we use are visual analog scales and Likert scales. So, with the visual analog scales, we're asking patients simply to mark a line anywhere on that bar that denotes how they feel about that question. So in this example, being comfortable. With Likert scales, we always present them with either a statement or a question, and it's more of a multiple choice selection. The responses then are pretty much provided. They just have to choose which one applies to them. And the reason that I shared that with you is for this next slide here is I would like to share a survey that was conducted that helps us illustrate not only why our measurement of comfort is important, but also how it correlates with overall patient satisfaction. Okay, and the survey also illustrates how physical and visual comfort play a role actually in overall satisfaction. And in this survey, in this study, we had 243 soft contact lens wearers enrolled. 101 of them were daily disposable wearers, and 142 were reusable wearers. And during this study, they agreed that over the course of one day, one entire day, 16 hours, that they would receive a text message every 2 hours. And that text message contained questions that took them about 5 minutes to answer. And the questions were, comfort and how's their vision and how's their overall satisfaction, those type of things. And, they just responded in the text, and then after 5 minutes stopped and went back, doing their business. Okay. So the survey showed some pretty interesting things here. So it showed that comfort decreases throughout the day on approximately 60% of the patients, which is shown there at the blue line on the bottom. And this finding is probably not new, since we typically see this in everyday practice. You know, it's a pretty common complaint, I think, that contact lens comfort decreases throughout the day. What we don't often consider, though, is that vision follows the same general trend, which is that yellow line on top. And consequently, overall patient satisfaction is reduced throughout the day, which is that green dashed line. Now, in regards to that blue comfort line that's on the bottom, you know, what are the symptoms that are actually driving that? That's important to us to know. Is it purely physical type of comfort issues, or is there a visual comfort component as well? So we asked them, you know, what type of symptoms are you having? And when it comes down to the patient-reported symptoms, the most common symptoms reported by these wearers were dryness, which is shown there in the blue line, which dryness is more of that tactile response that I would consider more of a physical experience. And that was followed very closely, almost hand in hand, with the symptom of tired eyes, you know, which is less tactile and more perceptual. It's more in line with what I would consider a visual comfort sensation. So these symptoms, both tired eyes and eye dryness, you know, both physical comfort and visual comfort actually mirrored the drop in contact lens performance throughout the day. Okay, so there was more to it than just physical comfort. Okay, and you know, it's important that we consider both physical and visual comfort concerns when fitting our patients with contact lenses, because you know, globally 68% report, you know, dropping out of their contact lenses for performance issues. Okay. And when we refer to a visual comfort with contact lenses, again, I'm going to refer to the more perceptual responses, such as eye tiredness or sensitivity or fatigue, eye strain. That's more in line what I consider visual comfort. And you know, I think visual comfort on the surface is largely intuitive. I think it makes sense. You know, we kind of define it as the feeling of ease, well-being, or satisfaction with the visual environment. And again, I think that's largely intuitive, but it's very hard to measure. Other than questionnaires, it's actually kind of a hard thing to measure that type of satisfaction. But where it plays a role is, you know, we've all had those patients that see 6.6 and they're very satisfied with their vision. They're very happy. And you know, the next person also sees 6.6 acuity, but they're not happy. They're unsatisfied with their vision. And you know, why is that? You know, and I think a major component is they're not visually comfortable. So I think it's important to know what contributes to that and what can we do about it. So on this next slide, I've put this table together. This is some main causes of visual comfort as they show up in the literature. In that first column there, patterns and contrast. You know, if we look at very annoying patterns or very poor chromatic contrast images, they're not pleasant to look at, and it can cause symptoms of eye strain and nausea, as well as headaches. And in the next column, glare. The glare is listed throughout the literature as a major cause for visual discomfort and can cause, you know, squinting and blinking less, and it certainly reduces our contrast, and it actually scatters light a little bit more. When we look at retinal luminance, this is just a broad category where it's just too much light. There's just too much. We tend to look away from those type of light sources. It can actually hurt. You'll see I have things listed there called the BCD and the VPT. The BCD is it's the borderline between comfort and discomfort glare. And VPT is visual photosensitivity threshold. They're really the same thing. It just depends on who's doing the research. So The BCD value is used a lot with architectural engineering, with lighting engineers. They use that measurement to actually determine how much or how many luminaires to put in a ceiling and how bright those luminaires should be for your office setting. And VPT, the visual photosensitivity threshold, that is often used in research settings. Moving over to wavelength, we definitely know that certain wavelengths cause more discomfort than others, particularly in the violets and the blues. And I will definitely be touching on that here in a little bit. Then finally, just uncorrected refractive error, eye muscle imbalances, looking at stereoscopic displays, that can also cause, asthenopia, fatigue, and headache type of symptoms. Now, what I'm going to more concentrate on is what I just boxed there in blue, because at J&J, we are able to influence most of these items, really thanks to new technology. And as lens manufacturers, we can directly impact variables such as chromatic contrast, glare, retinal luminance. We can now filter wavelengths, and of course, we can correct ametropia. That's a given. Okay. Now, this slide illustrates factors that we believe contribute to visual comfort, and they can be divided into three main buckets. So the first one being discriminating vision, which includes items such as vision quality, stereopsis, and motion detection. The second main bucket is visual endurance, which includes environmental conditions, okay, contact lenses, and ocular conditions, such as dry eye. Then finally, spatial vision, which includes the topic of visual fields. Now, given the time that we have, I will actually focus the rest of this talk on vision quality and light and how those contribute to visual comfort. Okay. So we believe that there's 5 essential elements to visual quality. Okay, and one of those is what we call understanding visual optics. And in a moment, I'm going to describe this briefly in terms of the point spread function. We also have to have optimal lens designs, which I will describe in a manner called lens wrapping. It might be new to you. I'll describe how we think about it here when we design lenses, as well as the importance of having a stable toric design. Optimal lens material, I will talk to that in terms of the pre-lens tear film. And when I talk about optimal lens manufacture, some really interesting data has come out on this that, I'm going to talk to that in terms of accuracy, in that what we design and what is actually made, how accurate is that? How well does that transfer over, and how does that impact our visual quality? Then finally, I'll talk about light filtration and certainly a lot of its perceptual advantages. So if we can talk about understanding visual optics, I mean, there's a lot of ways to describe image quality. You might hear a lot of things like the MTF or the straw ratio or the root mean square error of an image. And honestly, that's, don't worry, I don't get much of that either. But the point spread function, I think, is largely intuitive, and I think that we can kind of focus on that for just a moment. Okay. The point spread function literally contains information about everything that happens from object space to image space, and this includes everything from refraction, higher order aberrations, and glare. And what you see on the screen is an object out here in object space. Exactly what does it look like back here on image space? How much is this actually spread? Okay. And we know that when an image is degraded, actually to the point where 2 point sources overlap, we just can't resolve them as being discrete. So if we know the point spread function, we can actually superimpose this over the object to simulate the image. And a simple analogy is a distant car headlights that we can place on this image. And the effects of aberrations and scatter could cause this overlap. and make it difficult to tell them apart, right? And certainly visual quality suffers if we have a large point spread function. And there's a practical example that I'd like to share with you. In this study, we had a control lens and a test lens, and this is the point spread function that was measured for both. And what we did is we took these lenses and we put them in the clinic. And here you can see we looked at logMAR visual acuity under low luminance high contrast and high luminance low contrast testing. And basically what this says is there was a statistical difference actually in favor of the test lens, that people could actually see a couple letters better on the logMAR acuity, which is great, but does it matter? Can the patients actually experience? So we let them wear the lenses for a couple weeks, and when they came back, they reported that the test lens with a smaller point spread function, that 82% of them said that their vision was either excellent or very good. Okay, and when you compare this to the control lens that had the larger point spread function, only 66% rated the lens as excellent or very good. So again, this is kind of going to illustrate that, you know, just a small difference, a seemingly small difference, actually makes quite an impactful benefit to the patient, almost a 20% difference in subjective scores. Okay, now I'll talk about optimal lens design, and I'm going to touch on that on two different concepts. One of them is the concept of lens wrapping, and then the importance of stable toric lens designs. So this slide illustrates that the impact of placing a spherical lens and a aspherical lens on an aspherical cornea. So the only thing that you see now is what's on top, and that's placing a spherical base curve on an aspheric cornea. Okay, and what we're trying to show here with this graphic is that this, again, this lens is spherical, and obviously the cornea is aspheric. And when this lens goes on and wraps, you actually see the color change in here, and that's a lot of stress that's being placed inside the lens. And through modeling, we kind of estimate what's the impact that this is going to have on vision. Okay, so this is where that just noticeable difference, that unpleasant rating comes into play, is that when we look at just noticeable difference, due to that stress of putting that spherical lens on an aspherical cornea, we know that it can have an impact of up to 3 JNDs. And just for your reference, a 3 JND equates to about a quarter diopter of blur, or about a 1-point change on the Likert scale. Now, alternatively, if we take a aspheric contact lens and put it on an aspheric cornea, we'll see that there's almost no stress that's placed in the lens. Okay, and the just noticeable difference is virtually eliminated. There's almost no effect, predicted effect on vision when that happens. So this is something that's a little bit behind the scenes of what some of our optical lens designers look at. It's really a more critical, thing for complex optical designs, such as like multifocal lenses. It's where it really comes into play. Okay, and this slide illustrates, you know, some of the real-world reason why stability and soft toric designs are essential, really, for visual satisfaction. On this video on the left, this is what your patients do when they leave your, you know, consulting exam room. Obviously, life has movement, it has contrast, it has color, it's dynamic. And your eyes are constantly scanning the environment. And it's important that a toric lens design keeps up with your eyes' movements. And on the right-hand side here illustrates a solution, right? It's a toric lens design that is stable with both eye and head movements. So, you know, why is this important? Well, I think this is, to many of you, is pretty self-explanatory, but if we have a toric lens that's just 5 degrees off axis, and this is illustrating a 2¼ diopter cylinder lens, that if it's just 5 degrees off axis, you can kind of see what it does to the image. It starts to kind of fuzz it out just a little bit. And certainly as you move to 10 degrees off axis, 20 degrees, and even 30 degrees off axis, the image quality just goes down. So clearly, a stable toric design is it's essential for visual satisfaction. Okay. And next, I would like to touch on some topics that we don't normally think about affecting visual comfort. And that's the importance of contact lens materials that do affect the tear film, as well as accurate manufacturing. Okay. There was a 2019 poster at ARVO that described this, this exercise here, that new lens materials in manufacturing had demonstrated an approximate 2-letter improvement in high luminance, low contrast logMAR visual acuity. Okay, so we always think about, the optical design and the front curve, back curve, and that type of thing, but there's actually more to it. There's more to it that that's impactful, that we can actually improve vision through other means as well. So of that 2-letter improvement in high luminance, low contrast acuity, about 18% was attributed to the pre-lens tear film. About another 18% was attributed to lens decentration. And finally, about 64% was attributed to an accurate manufacturing. So each one of these, I just want to touch on really quick. If we look at the pre-lens tear film and why this is important, you see the impact of 2 identical materials here, Edafilcon A and Edafilcon A with PVP. The materials are identical, except obviously the addition of PVP in the bottom one. And these images were taken through an aberrometer. So what you see in green would show a tear film that's considered stable, whereas when you get into the blues and the reds, that's when it becomes more thin and unstable. And clearly adding PVP to the lens enhances the pre-lens tear film and literally makes it more stable. So, why is this important? And well, if you recall, that the tear film interface between the tears and the air, that accounts for 2/3 of your eye's refractive power, right? So you get small fluctuations in your tear film, and that can definitely, result in fluctuations in your vision, okay, which would decrease your visual satisfaction. Okay. This data was from a 2018 paper that shows the effect of lens centration that it can have on our visual acuity. So in this paper, they showed that if you have high luminance, low contrast charts, and you decrease you decenter a lens radially. So if you look at the x-axis there, I don't know if I can get my mouse to show. Yep, if you look at the x-axis, this is 0 decentration, right? And you can decenter it laterally more and more. And as you do that, there's actually a predicted loss of high luminous, low contrast letters. And when you get out here in this range of 0.9 millimeters to 1 millimeter, that's 5 letters. That's 1 line of logMAR acuity. So it illustrates how important it is that lenses center. And we know that if it does decenter, it's those off-axis aberrations that are generated that causes this decrease in visual acuity. But that's an entire line, and these are spherical lenses, not multifocal or toric designs. Okay, so it is important that we keep lenses centered on the eye. Okay. And this slide will illustrate what happens when we take the exact same contact lens material and just simply manufacture it 2 different ways. Okay, so in this study, the new manufacturing technique it reduces residual sphere, it reduced residual cylinder power, and higher order aberrations compared to the conventional method. And the other way to think about it is it manufactures the lens more accurately. And in clinical studies, this results in a 14 to 30% increase in the area under the contrast sensitivity curve, which when you put this on patients and you have them wear them, makes a meaningful visual difference to them. So again, this illustrates where, sometimes we can make what seems like a small difference in contact lenses, but it makes a significant impact to the patient's own eye. Okay. Now I would like to take the remainder of this time and discuss how light impacts our visual comfort. Okay. And this is the topic that's near and dear to my heart. So, why do we wear sunglasses? You got to always ask the questions why, right, in research. So we all have placed on sunglasses, right, in a bright, sunny environment. You go to the beach, you put the sunglasses on, you feel more comfortable. But did you ever stop to wonder what's going on that makes you more comfortable? What psychophysical aspects are actually being influenced or affected? What's going on that actually makes us more comfortable? Okay. Well, one thing that we know is that at constant luminance, okay, patients respond that shorter wavelengths are less comfortable than longer wavelengths. Okay, and this is shown here in this graph by Flanagan. And this bottom line here shows multiple different light sources. So like a blue light source, a green, a yellowish light source. They're all at the same luminance level, but yet patients respond that the ones down here lower are less comfortable than the ones higher. This scale is more comfortable as 9, less comfortable as 1. So you can see at constant luminance, there's definitely a difference in perceived comfort. And then if you go, just make everything brighter, you actually see the same pattern. If you make it brighter again, and then brighter again, and you'll just see, well, actually just the opposite. It's actually lowest luminance on top, but the gist is it's all the same pattern. And the only thing that's different between these is the luminance level, but the same pattern always exists, that the lower end, the shorter wavelengths, are more uncomfortable. I just highlighted this area here because it's going to show up in a couple other slides. This is the blue light hazard range. This is the range that's defined by ISO to be approximately 400 to 500 nanometers. And this is where there is reported some actinic activity as well as some possibility of retinal damage lies in this area. Okay, so that's just in there for reference at this point. Okay. This graph shows the spectral output of typical indoor lighting, which is just hugging the x-axis right here. So if you look at this green line, which is almost flat, this is actually the spectral output of digital devices. I think this was a spectral radiometer output of an iPhone. And then this yellow line is just indoor fluorescent lighting. And when we overlay that blue light hazard area between approximately 400 and 500, you can see that there is some energy that's being emitted by digital devices and indoor fluorescent lighting. And you often hear now of blue blocking lenses, right, for indoors and for computer use, which, I mean, on the face here, it does have merit because there is energy being emitted in this range. But kind of the point of the slide here is that, if we're going to have concern about this blue light here, then we really need to have concern about what's going on outside. Because this graph here on top is the solar radiance. Everything's plotted on the same scale, and you can see it's literally hundreds of times more blue light that you get outside than you can ever do inside, okay, with normal lighting and normal digital devices. Okay. Next, I want to talk a little bit about glare. And, glare occurs when the luminances or luminance ratios are excessively high in relation to the state of adaptation. That's just a Nancy definition. They also describe the luminance ratios, which is kind of important to know. The luminance ratios of an object here circled in green. It's how bright is our object compared to how bright is the glare source. Okay, and the type of glare is determined in part by where this glare source is. So if it's closer to the object, that starts to disable your vision, which we'll talk about in just a moment. You know, but also not only where it is, but how many of them are there, right? You can have multiple glare sources in the same scene, and how big it is. So if you have a very large glare source, that matters as well, okay? But when the glare source tends to be off to the side, that's when it just tends to be more annoying or just kind of uncomfortable to your vision. But again, when the glare source gets closer to the center, that's when it starts to impact what we're trying to do. It starts to disable some of our vision. So if you look at discomfort glare real quick, again, it's that light that is bothersome, but we can still perform a task. So the light's coming in the car here from the side. And one of the ways that we cope with discomfort glare is to, you know, look away. We can shade our eyes or even just squint our eyes, okay? That's usually the response to that. And I just put the slide in here because I think it's really interesting to note that squinting may have evolved as a protective response to damaging light. So what you see in this graph here is this red line was generated by hand back in 1976, showing the amount of retinal damage that occurs for a given wavelength. And you can see that the shorter wavelengths are definitely more actinic, they're more damaging, more active than the longer wavelengths. And then back in 2003, Jim Stringham did a study where he looked at how much do you squint in response to wavelength. And that's what's shown here in the black line. And obviously they correlate very well, okay? So clearly, you know, we squint more heavily to wavelengths of light that are more damaging. And there's that blue light hazard range again, just for reference. Okay, and disability glare impacts our vision primarily through intraocular scattering. Let's see if I get this up. The image of the target largely passes through the eye, you know, unaffected. And the off-axis glare source, however, can have a tremendous impact on our vision, primarily through intraocular scattering. And we know that intraocular scattering glare issues just increase dramatically with age and eye disease and changes, you know, to our orbit even, and even some neurological conditions such as migraine. It just becomes a huge annoyance. And, you know, what's kind of illustrated here is if you look at the, here's the target over here, but the image, when you look at it, kind of looks like you're looking through a veil, which is why sometimes this is also termed veiling glare. Okay, and just a quick note about photostress. Sometimes, you know, light is just too bright and photostresses the retina, and it gives us like that temporary after image. And this is often associated with discomfort and pain. And really the ability to recover vision after photostress is dependent on not only the health of the retina, but the intensity of the light that caused the photostress. And what's important to know here is that the intensity of that light that causes photostress, we can do something about. We can actually filter some of the light to make photostress, the impact of photostress, less impactful. Okay, I'd like to talk now about a concept called chromatic contrast. Chromatic contrast, we can measure this in a lab, and it allows us to discern actually more detail from within an image. And although we nearly always measure contrast sensitivity with achromatic gratings, the black and white gratings, our world is, you know, filled with colors that we simply don't measure. Okay, and again, color just serves to provide just better detail in terms of detecting edge of objects. And, you know, chromatic contrast can be influenced and it can be improved using colored filters. So I'd just like to take a moment, just look at the basis for this and to show you an example as well. Okay, so here on the screen we have two gratings, you know, one achromatic and one chromatic. And they're both shown here on the same X and Y scale. And if we draw the contrast sensitivity function on both of these, what we can see here is that on the chromatic contrast sensitivity function, we are actually showing, here we're actually showing more low spatial frequencies that are captured by the chromatic gratings than we do with the achromatic gratings, right? So we see that that chromatic contrast actually adds much to our low spatial frequency perception, and this is like for the coarse global shape of a mountain or a house, okay? What's also interesting is the low spatial frequency component. It's also known that it's critical for accurate speed perception. So chromatic contrast actually aids in motion detection. Okay. And during my research in this, it took me a while to really appreciate this. But when we look at that image that's on the left, the bare naked eye image, we consider this the natural image. But when you do this type of research long enough, you come to realize that it's not. It's really corrupted by a lot of the issues that we've talked about already, like scattering and glare and reduced chromatic contrast. And in this scene, if you look at that image on the right, it's just looking through like a yellow and green filter. And what it does, it's used to darken and enhance the color of the grass and give some color variation in there that you just don't get on the left-hand image. And obviously looking through that type of filter, this makes the details easier to pick out. You can start to see the undulations of the grass surface and the visibility of the cloud layer that you really, kind of miss on that image on the left. Okay, so this is how chromatic filters or spectral filtering can actually make things more comfortable to see, and actually a little bit more realistic. Okay, so how is visual comfort assessed? Well, similar to physical comfort, the visual comfort experienced by a patient can be assessed with a questionnaire, subjectively. But importantly, how we react to visual stimuli, we start to branch into the field of visual psychophysics. And within that field, there are a lot of well-known scientific measurements or tests that we can have at our disposal. And the other way of putting it is, we can actually start to measure various aspects of visual comfort by testing the threshold of various psychometric tests. So let me explain what I mean by that. So measuring visual comfort. This is an optical bench system that was developed by our colleagues at the University of Georgia here in the US. And I'm not going to go through all this, but just to briefly ground you on what we're looking at here, this kind of box-shaped thing here on the right is a light source. And this light source is a Xenon Arc Lamp. And this light source was specifically chosen because how closely it matches the spectral output of midday sunlight. It's very similar. So the advantage of that is that we can test indoors in very controlled environments what the patients will see when they step outdoors. Okay. So when this light gets turned on, the light is sent through all these filters and lenses, and finally it's viewed by the patient sitting over here on the left-hand side. There's also a video camera that's mounted on this breadboard, and what it's doing is it's actually recording the eye's reaction during testing. Okay, so if you're a patient sitting over here on the left-hand side, what do you see? What are you looking at? Well, when you sit there, you actually see this kind of image. There's a central grating that's in the center, and it's surrounded by this black ring. And that black ring is actually the light source. Okay, so one of the measurements that we do is with photo stress recovery time, patients are instructed to look at the central grating. That central black circle of light will flash like this, and it'll stay on for about 5 seconds and then go away. And then what we do is we measure how long it takes for their vision to return, right? It's the classic photo stress recovery time test, okay? So that's one of the measurements that we collect. The other thing that we collect here is discomfort glare. And what this is and I alluded to it earlier when we talked about discomfort glare, but when you're in the presence of a really annoying bright light source, you have a natural reaction to look away, to turn your head down, to shade your eyes, and almost always you squint. You almost always squint your eyes in that presence of a bright light source. So during the photostress recovery test, during that 5 minutes of flash, remember there's a video camera that's recording what the eye is doing. So 1 second into the 5-second flash, they stop the video and they record that vertical distance between the upper eyelid and the lower eyelid. And that is, they measure the degree of squinting. Okay. A third measurement that we get from that instrument is called disability glare. And it looks similar. Subjects are still instructed to look at the central grating, but there is this dark surround. And in this test, the light, the dark light around is actually increased, and it keeps increasing until you can no longer see that central target. And the amount of light that's required to obscure that central target is recorded, and that's your level, that's your intensity of light that's needed to disable your vision. Okay. And finally, we have that concept again of chromatic contrast. And in the study, they used a green center target surrounded by a blue surround. And this was specifically chosen, the blue and the green, because it represents the most common color combination that's seen in nature. And this has been known for a long time that blues and greens are seen all the time. Think about green trees against a blue sky. You just see it all the time. So it was a way to try to make the test more ecologically valid is by picking these color combinations. But in this test, it's the same type of thing as disability glare. The blue light was increased until you can no longer see the central green target. Okay. Another thing that we look at as a way of objectively measuring aspects, of visual comfort is measuring dysphotopsia, which, as you know, is just the fancy way of saying halos and starbursts. So in this setup, this back panel here has a small hole cut in it. It is back illuminated, and that light travels all the way to the front, and the patient is seated here on the right-hand side at the front of the image. There are movable calipers that are shown here with the red arrows, and during testing, these calipers are moved either in or out, and it physically measures the diameter of the halos and the starbursts according to the patient feedback. So, if we look at these clinical measurements, if you look at halo here on the left-hand side, what's done is those calipers are brought in until the patient says, yep, it's right there at the edge of the halos, and then they read it. Okay, and obviously the measurements are repeated. Same type of concept for starbursts, except this time they're only coming in to the edges of the spokes. Okay, and then finally over here with 2-point light scatter. This was a really interesting test because what they did is they took 2 back illuminated point sources of light, and then during testing they slowly spread them apart until the patient could see that they were 2 distinct images, that there was black in between them. Okay, and then what they did is they measured that distance between the 2 points of light. So if you're wearing a filter that actually reduces the amount of light scattering, that spread will actually be smaller, right? Okay, so these are just a few of the psychophysical measurements that can be done and that we have done already. Okay, so just to kind of wrap things up here, in summary, what exactly makes our 6'6" patient unsatisfied? Well, if you look at the physical discomfort symptoms, we have the dryness and the itchiness and those type of things. They're more tactile, more things that are more related to touch, in my opinion. And we know that we can mostly address these issues with proper lens materials and lens designs. Visual discomfort symptoms, there really are responses to visual stimuli. We can feel tired, or we can feel sensitive to light. We can get headaches. And these symptoms can be addressed, with lens designs made accurately and through filtrations of the most bothersome wavelengths of light. All right, and taken together, our overall comfort experience can certainly help turn our 6/6 unsatisfied patients to satisfied patients. Okay. And just last thing, what should you do differently when you go back to your office, when you're allowed to return back to your office? Well, just keep in mind that 60% of patients feel a decline in their comfort, vision, and satisfaction throughout the day. And this is driven, as we would assume, by dry eyes, but please remember it's also driven by tired eyes. And it's just something we don't normally ask. And if we have a physically and visually comfortable contact lens to offer them, then it can certainly help turn a 6/6 unsatisfied patient to a satisfied patient. So for actions, simply don't ask your patients whether or not they're light sensitive. You get a very poor response doing it that way. I think we know that if you just ask that question, it's about 1/3 of patients will say, yeah, I'm light sensitive. But if you ask them, hey, are there moments during your day where you're bothered by bright light or where light is bothersome to you? Such as viewing digital devices or driving at night or playing sports. And then you're getting a lot closer to almost 65 to 70% response to say, yeah, I'm bothered by that situation. Okay, so obviously we would recommend a light filtering contact lens to be worn. And if the patients wear a lens like this, it really needs to be worn for a couple weeks. Okay, and this is just so they can try it in all the different lighting environments, so they can really begin to appreciate the seamless benefits. Okay, and it's often not until they don't often fully value and appreciate light filtering contact lenses until you actually take it away from them. So sometimes a comparison back to their habitual correction might actually be helpful. Okay, and I think that's it. I thank you and everybody for your time. I would be glad to take any questions.
Perfect. Dr. Butch, thank you very much for excellent presentation. And we have a couple of questions now. So there's the very first one related to, we have received, in fact, at the beginning of the session. And the question was related to study you have been showing at the beginning. So the question was there a difference in comfort with daily disposables and reusables?
Yeah, that was really interesting too, because we saw it happen with both daily disposables and reusable wearers. And again, that declining graph that I showed, again, that represents about 60% of the population, meaning that the other 40% were more like they just maintained. They were pretty level throughout the day. So it wasn't everybody, right? It's about 60% of the people do decline throughout the day, but we did not see a difference, not like what you would expect between daily disposables and
reusables. Okay, perfect. Thank you very much. Another question is related to any available resources. Are there any available resources I can potentially use for my patients? I can refer to my patients in my contact lens practice?
I'm sorry, references for what?
References to physical and visual comfort, what I can use when, I'm assuming the question is related to what I can use potentially when discussing with my patients.
Oh, discussing, yeah. Yeah, that's been an area of discussion for quite some time here internally, is we're looking for simplistic ways that we can demonstrate benefits of a lens while in office. I have to be honest, that we're still trying to find that really good solution to that. We know that if you take patients, you put lenses on both eyes and you take them outside, it's a very subtle change. Like if you're wearing the photochromic lenses, it's a very subtle change. They don't actually know or appreciate it. But then if you were able to take them off, they're like, oh yeah, there it is, that type of thing. But yeah, we're still working on a demonstration that we think would be applicable, nothing that would take a lot of space in the doctor's office, have a very small footprint, but be very impactful. And we've had several ideas, probably 15 ideas come through, and we're still trying to refine that. So the direct answer is we don't have anything available yet, but we're certainly on it.
Mm-hmm. Perfect. Thank you very much. Another question, in fact, what is the clinical and product relevance of the visual comfort?
I'm sorry, the clinical relevance of
the relevance of the clinical relevance of the visual comfort.
Oh, just to make that was yeah, because to be visually comfortable, it's really another way of saying just being visually satisfied. It's being very comfortable with your vision. You know, that's the whole point of why I think patients that can see 6/6 or 20/20 acuity, why some of them just aren't. They're not happy, although they can read just as well as other people that are happy. You know, and why is that? And I think it's when we start looking at what's the very best materials that we can use, what's the best optical designs we can use, can we make sure that the lenses are made exactly right, can we filter the right wavelengths that are most bothersome to patients. I think that's the whole, you know, collection of visual comfort attributes that we can impact to flip that patient from being unsatisfied to satisfied.
Mm-hmm, mm-hmm. Perfect. Thank you. And of course, there is a lot of questions related to AKB Oasis with transitions. So one of them, and I believe that it's really connected to what we have said or what you have been presenting today. In fact, why do I need, you know, these type of the lenses, meaning the transitions, if I can wear sunglasses?
Well, that's right, but you can't you can't wear sunglasses everywhere, right? So what's really interesting, and we've presented this data elsewhere, but you know, I'll bring it up here, is you know, when patients wear the photochromic lens outdoors, and you compare it to non-photochromic lenses like Oasis, I mean, you get like a 6-to-1 preference for the photochromic, which is what you would expect, right? That's where it gets the darkest, and that's where you expect the biggest benefit. But what gets glossed over a little bit, and I wish it wouldn't, is when patients are indoors, and when you look at how does the photochromic lens compare indoors to a non-photochromic lens. And we're getting 4-to-1 preference for general indoor use, and you know, 4-to-1 preference for use on a digital device, and we're getting 3-to-1 preferences, you know, for use while driving inside of a car. And these are all you know, compared to AccuView Oasis, right, which is the world's leading contact lens. And so you know, there's going to be situations where you just can't wear sunglasses. You can't wear them, or you typically don't wear them indoors. Or just you're walking out to the mailbox, or you're at an outdoor wedding, or you know, there's going to be situations where you just can't wear sunglasses. Or even playing sports is a huge thing. Think about, you know, playing soccer. If you have sunglasses on, there's just applications where the lenses would have a benefit. And my point of talking about the indoor benefits is, you know, you typically don't wear sunglasses indoors, but you can still definitely get a benefit with this lens if you do wear it indoors compared to Oasis.
Perfect. Thank you very much. And the very last question I'm going to keep at the end of the Q&A session is if we can ask you what are the new projects you work on and you can share with us.
Yeah, I can't share that. We have, it's a good thing you can't see my board over here. I have a lot of projects that we're working on that all has to deal with light filtration, and you know, they're unfortunately kind of close to the vest right now. They're proprietary.
Okay, perfect. Thank you very much.